In this video, I will explain the Euler's methods for numerically solving first order differential equations. We are interested in solving first order differential equation because once we know how to solve first order differential equation, we can easily construct methods to solve higher dimensional, higher order differential equations, and also system of coupled differential equations that we will see during the due course. Euler's methods are actually the simplest methods for numerically solving differential equations, and even if they're not used too much for solving differential equations in many research problems, but still they form the foundation, or you can say the basic framework for the numerical solution of differential equations. So that's why it's important for us to understand these methods. So in this video, I will discuss two basic Euler's methods. One you can just call Euler forward method or just Euler method, and the other one is called Euler's backward Euler's method. So let's begin with the simple or the forward Euler's method. Suppose we have a first order differential equation to solve, which can always be rearranged to be written like this. The first derivative is equal to some function which has both x in general and y in it. So we can easily set up a numerical method to solve this equation if we exploit the definition of this derivative. So using forward difference for the definition of this derivative, we can write x plus h minus f of x over h. So using this method, we can set up the solution of this differential equation. Now, in this video, I'm interested in solving initial value problems. Initial value problems are the problems where we are specified an initial condition for that at a particular value of the independent variable, the value of the dependent variable is given. Suppose we are given this, and what we have to do is find the solution of this equation for the values of x in, let's say, an interval from x to x capital N. So this is some interval in which we want to find the solution, and we are given the value of this function at the starting point, at the initial point of this interval. So our job is to find y of x, where x belongs in this belongs to this interval. So to use this forward difference to approximate the derivative, let's divide our interval into n number of points: x naught, x1, x2, some xn, xn plus 1, and some up to capital Xn. So I have divided this interval into n plus 1 number of points. And the difference between any two consecutive values is, let's say, delta x, and many times I will simply write it as h. Now, suppose we pick two arbitrary points, two arbitrary successive points from this partition of this interval, say xn and xn plus 1, and we can write the derivative of this function at this point using these two values of x as dy by dx. And sorry, there's an error here. If this is dy by dx, we need to write the value of the function here. So dy by dx can be approximated to first degree in h as this difference divided by xn plus 1 minus xn. And if I introduce a notation that y of xn plus 1 is simply yn plus 1, and y of xn is simply yn, and this delta x, let's just write it as h. So this is the derivative of this function. So if I substitute this over here, what we get is yn plus 1 yn h f of xn y. So essentially I evaluated this equation at xn. At xn value of y is yn, and at xn the derivative using the forward difference method is this. So putting here, this means that I can rearrange it. This h goes there and this yn comes on this side. So this is the Euler forward method of just Euler's method for approximating solution of a first order differential equation. You see, we can easily set it up in any computer program. We know the initial value x naught, y naught. We put x naught, y naught here, y naught here. We can compute y naught quickly so we don't need to compute y naught because y naught is given. So we use these initial values here to compute y1. Then once we have y1, we put x1, y1, y1. We compute y2 and so on, and we can get this sequence of values of y which approximate the actual solution y of x. Let's see how we can imagine this method geometrically. So what it does, that suppose our actual solution is something like this. So this is the actual solution that we are trying to find. What we are given only is the slope of this actual solution at every point x. So let's say we are at this arbitrary point xn, and by finding f of xn, essentially what we know is this slope, which is xn yn. So with this method, what we are doing, that at the next point xn plus 1, we are adding this difference, and this is nothing but slopes times this h. So this is h, and if I multiply this h with slope, I should get this length, assuming that this is straight line, which is mh. So all we are doing is adding, so this is point yn, and this is yn plus 1. To get yn plus 1, we are just adding this part, slope into h into yn. So at this point then, when we reach the next point, to find the point later on, we are given this slope. So we approximate a straight line passing through this point with the same slope as this, because we know slopes at each point. So by approximating this curve with another straight line here and using this slope, we can find the next point and so on. So at each point, we draw it here. If we have actual solution like this, our numerical method is, trying to approximate the solution and successfully trying to go closer to this. So this is how this Euler's method work. So of course we can easily show that this solution is approximately equal to the actual solution with a proportionality constant of h. So the smaller is the h, the smaller is the error of this y from this actual solution. So our accuracy of error is proportional to h, because we are using this first order definition for this derivative. The second thing is this, that if we want our numerical solution to match actual solution, we need to have this h as small as possible. Sometimes it works okay, but sometimes it can run into problems because of accumulation of round-off errors when we make x smaller and smaller, because when we have to make x smaller, effectively we're increasing the number of points in this interval where we have to find the solution, and more points mean we have to do more computation that can increase the round-off errors in our approximate numerical solution. Okay, so this was Euler's basic method. Let's now see the second iteration of Euler's method. It's called backward Euler method, and you will see why. It's actually one of the methods in a class of methods which are called predictor corrector methods, and we'll shortly see why this new name is there. So let's get back to our original equation. So if instead of approximating the derivative as the forward difference, if we use the backward difference to compute the, someone keep on writing this f of x, but y of x. If we use the backward difference, which means that to find the derivative at x, I use the value of y at x and the value of y at a point before x, then what we get is a method which is called backward Euler method. So in the same way, if I want to compute the derivative at x is equal to xn, this becomes y xn, y xn minus 1, sorry, xn minus 1, h, and if I now see this equation, this will transform to yn minus yn minus 1 h f of xn yn, which means that yn is equal to, so this h goes there, this goes to the other side, n minus 1 plus h f xn yn. So this is the equation that we get. There is of course a trouble that to compute value of y at n, we also need this function at yn, and we'll see shortly how we can overcome this. But before that, let me instead of writing it this way, write it this way. If I just take instead of evaluating at n, if I evaluate it n plus 1, I can write it like this for easier comparison with the previous method, xn plus 1, yn plus 1. So this is the equation that we have to solve. Remember, initially we are given x naught and y naught. So in the simple Euler method, we were able to find an equation where the next value of y depended on the previous value of x and y. But here we have an implicit equation for yn plus 1. Remember, these x's are all known, x1, x2, x3, etc. because this is the partition of interval. So this isn't a problem. The problem is this. So this is an implicit equation, and there are several methods that we can use to find yn plus 1. Maybe we can, for each x, we can use Newton-Raphson at each point to solve this equation for yn plus 1, and maybe other methods. However, they could become complicated or cumbersome, but instead of that, we can find the solution in a simpler way. If we use some coarse method or some simple method to first approximate this yn plus 1 and then use that approximate or guess value of yn plus 1 on the right side to compute this side and then find this new yn plus 1. So what we do, we can, and one choice for that simple method is actually just the forward Euler method itself. So what we do that at each point, we first compute a guess value of yn plus 1 using the Euler method. It is yn plus hf xn y. And now, because this side is okay now, we know x and y at the previous point, we can put them here and we can compute the next y value, which I'm now calling guess value. Once we found this guess value, we can come back to our backward Euler method and put it here, xn plus 1, and now it was yn plus 1, let me just use yn plus 1 guess value. So with this way, we can compute the next value of y using the guess value of y at that point, which was computed from Euler method. So to set it up in a program, we begin like this. Let's say at n is equal to 0, x naught, y naught is known, put them here, compute y1 guess, use that y1 guess, y naught, and x1 here, and compute y1 again. So now you see why we call it predictor corrector method as well, because this sort of predicts the value of y, the next value of y, and then this corrects that value of y. So using these two equations, we can keep on getting next approximate value of y at each point. We can see it geometrically working out like this. Let's say this is this. So suppose this is our actual solution. So we start from here, x naught. So we first use this forward Euler method, that we draw a straight line here, and then let's say this is our x1, and the simple Euler method gives us this value of y. So this was y naught, this is y1. So what we do, that we take this value of y1 and this x1 and compute the slope again. So this is the slope, this is the new slope, and we use another color. So this is the next slope. So once we know the slope at the next value, we come back here and we sort of use this slope at this point. So this is our starting point y naught, and we add this part. So this is now this part. So essentially what we are doing, that we are still approximating the actual solution by a straight line, but instead of using the slope of the actual function at this point, we are using the slope of the function at the next point. So we computed the slope here, approximate slope, we brought that slope here, and then using this slope we computed the next value of y. So now our corrected value of y is something like this. So with this way, we can actually keep going around the actual function instead of just going on one side of the function. So that's why this gives us a better approximation of the solution of the first order differential equation or not. Of course, we can easily see that the error rate of this function, this method is also proportional to h, but this turns out to be a more stable method than the forward Euler methods. Thank you.